By analyzing time series data, that is, observations made sequentially over time, epidemiological data analysts can spot trends and patterns that can inform public health decision making. In this lesson, we're going to use ggplot and other tidyverse tools to visualize time series data and effectively communicate insights. So let's get started. So here is our list of learning objectives. If you like, you can pause the video and read through these, but we're going to come back to them at the end of the lesson. So let's get started thinking about line graphs for time series data. We're going to examine tuberculosis notifications in Australia over time, comparing those notifications in urban and rural areas. And a notification is simply a reported case of a disease to public health authorities. So let's start by doing some data preparation, aggregating and pivoting our dataset. We're going to start by loading and inspecting this Australia data. So we run this line of code, and then let's try to view TB data Oz to see what's inside of it. Since it's super abbreviated, I will view it inside of a view console here. So as you can see, you have the period. Each period is marked by a year and a quarter. The number of cases of TB in the rural regions of Australia and in the urban regions of Australia. And this data goes from 93 all the way to 2022. So quite a rich data set there. So like I said, the data set includes period, which is the time in quarterly format, rural cases, and urban cases as well. Let's go ahead and try to visualize now annual TB notifications in urban and rural areas. Notice that it's in quarterly format, so we have to get it from quarterly to annual somehow. So to do that, we're going to first extract the year from the period column using the str sub function. So let's go ahead and try to do that. We take TB data Oz, and then we're going to pipe it into a mutate, where we're going to take the year as equal to str sub of the period, and then characters 1 to 4, because years have 4 digits. So now let's go ahead and run this and see what that looks like. So the year column now has been extracted. It's a bit hard to see again, so let's pipe that into a view so we can look at the full data set. So now you see that the year is extracted from the period. However, you will notice if we remove this view that the year now is a character. We need to change it to a numeric. So we pipe into another mutate and we say year equals as.numeric mutate, year. And then that gives us the value as a numeric. Okay. So next now we're going to try to aggregate the data by year using group by and summarize. So let's see how we do this. We're going to assign a new object called annual data Oz, and that's going to be the value of TB data Oz. And we first extracted the year from the period. Now let's go ahead and group by year, and we're going to pipe into a summarize, in which rural here is going to be equal to the sum of cases in the rural regions for each year, and urban is the sum of cases in urban regions for that year. So let's go ahead, run this, and view our annual data Oz dataset. So now as you can see, you have each year, and then for the rural areas, you have the number of cases, and the urban areas, you have the number of cases as well. So now we can go ahead and make an initial line plot with two geomes, one for urban and one for rural. So let's go ahead and do this. We're going to take this annual data Oz object, and we'll pipe it into, or pass it into ggplot plus geom line. Okay, and maybe we'll put our aesthetics in here, inside of the ggplot. Our x-axis is going to be the specific year. Okay, and our y-axis, actually I changed my mind. Let's put the aesthetic inside of geom line. Okay, so we're going to put this aesthetic here. Our x-axis is year, and our y-axis, first of all, will be rural. Okay, rural. And I've forgotten how to type. Live coding is quite difficult. And then we'll do another one with urban cases as well. Okay, so hopefully that makes sense. We have these three variables here, year, rural, and urban. And one line will plot rural against year. The other line will plot urban against year. So now we can run this and view our plot. And as you can see, you have those two lines separated there. And if you wanted, you could set them to specific colors. Here we could say color equals maybe blue. And here we could say color equals maybe red. And now we have those two separated colors. However, this code is not really ideal, okay, because it has unnecessary code duplication. And consider now if we try to add additional geoms such as points or text. So here we have just one geom, it's a line, and it's duplicated. And maybe that's fine, but if you try to add now maybe points and text, then you can see you have so much duplication, so much unnecessary code here. Okay, so let's try to run this bit. You can see we have a good plot, but the code is quite duplicated. Okay, and now imagine if we had more than just urban and rural to plot. We had urban, rural, remote, foreign, and some other categories. This would be a lot of code. So that suggests that maybe what we're doing is not really ideal. And indeed, that is the case. This is not the ideal way to plot this. What we really should do is use pivot longer from the tidyr package or from the tidyverse to reshape the data for easier plotting. So let's go ahead and see how we can do that. We're going to pivot and then do some renaming. So let's grab our data set now, annual data Oz. Okay, and let's give some space. So now we're going to pipe this into pivot longer. And the calls argument in pivot longer helps us define which columns we want to pivot. And that's going to be rural and urban in this case. Now if we run this line of code, we can see now that it has pivoted, although it's a bit hard to see. So let's pipe that into a cable function to print it nicely. So here we have 2 rows for each year, separated into rural and urban in this name column, and the values for rural and urban are in a value column. Now let's finally rename this, or rename those last 2 columns. We're going to change name to region, so region equals name, and we change value to cases, so cases equals value. And let's pipe that into cable one more time to take a look. So here we can see now we have region, cases, and the year. So that looks very nice. Finally, we're going to store this as oslong, and we're going to pipe that oslong object into a ggplot in the next section. So now we're going to try to make a basic grouped line graph. And because we've created this long version of the dataset, we have a better way to plot. We can map color and the group aesthetics to the region column that we just created there. Okay, so let's see how we're going to do this. We're going to make a line chart of oslong with x equals year, y equals cases, color, and group equals region. So let's grab our ggplot and put oslong inside of that. And then we say plus geom line. And we can put our aesthetics in here, or we could have put them into ggplot. Let's leave them in here for now. We say x equals year, y equals cases, color equals region, and group again equals region. Okay, and we can simply run this line of code, and in that single almost one-liner or two-liner, we have created what we tried to create above, with region and urban colored differently. Okay, so this is very nice. Now, because of the thing we have set up now, we can add points and text labels with less code. So all we have to do to add point and text labels is we're going to grab this line of code and let's paste it here. And because we want to add points and text labels, these are going to mostly inherit these aesthetics. So I'm going to take the aesthetics and put them back into ggplot. Let me just show you what I mean by that. So if I type here plus geom point, and I run just this here, geom point is missing some aesthetics because we gave the aesthetics directly to geom line. So if we want to do multiple geoms, we should give the aesthetics to ggplot, and now geom point can run like that. So now you have those points at the specific dates when these things were recorded. And we can also add text labels as well. So geom text, okay, and we're going to give some fixed aesthetics here, size of 2. And that'll make them a specific size that we want. We missed a label, sorry. So we need a mapped label here, where we have label is going to be equal to the specific number of cases that we're counting. Okay. So now that we run this, you can see that you have those text labels there. Of course, they are overlapping on the points, so that's not great. So we're going to add a fixed aesthetic of nudge y and fix that to the value of 20. So that'll nudge each point 20, or each text label 20 values upwards. Okay, so now that looks a lot better. Now with that information in hand, try this practice question where you import a dataset, use pivot longer, and then create a plot with 2 lines for different types of TB cases. So pause the video and try that out. Now let's think about some aesthetic improvements we can make to our line graphs. So we're going to try to focus on enhancing the clarity and the visual appeal of these line graphs that we're creating in this lesson. The first thing we're going to think about is reducing label frequency. So remember that when we left off, we had this plot, but we had some small text labels there, and these would be kind of hard to read in a public-facing plot. So let's take a look at our plot. So this is what we had. And while you can see this on this big screen, imagine if you were trying to print this in a report where it had many other graphs in tandem. This would be quite hard to read. So let's see if we can try to squeeze those labels a little bit larger. So one thing we could try to do is just increase the size. So maybe we can try size of 3 or 3.3 maybe. But you'll see that this starts to overlap with each other. So that's not so wonderful. So what can we do instead? What we can do instead is try to display labels for only certain years, certain key years. Okay? And to do that, let's try creating a dataset with only even years. And so we'll plot every other point rather than every single point. So let's see how we can do this. Okay? To do that, we're going to create an object called even years, which is a subset of oslong that only keeps even years. And we'll use this modulo operator, which is a way of saying, is there any remainder when you divide by a number? So we'll check whether there's any remainder when we divide by 2. And if not, that will be equal to 0. And that will help us select even years. There's some simpler ways to select even years, or some maybe more intuitive ways. But this way is quite robust. So let's take now oslong, and we're going to pipe that and filter the year column, where year, let's see, filter year modulo 2. Modulo 2 is equal to 0. Okay, and let me just print oslong year, just to make sure I haven't left you behind with this modulo thing. So oslong year, as you can see, we have 93, 94, and so on. So 94 divided by 2 will have no remainder. So 2 will 96, so 2 will 98. So that's how we get this sequence. You could also do maybe repeat a sequence from 94 to 2022, skipping every 2. So that's another way to do this thing. Okay, but we use the modulo because you should know it as a programmer. So filter year modulo 2 equals 0, and that'll give us the even years, okay, which as you can see, this is now just 30 years, where oslong was 60 years. So we're good there. And now we're going to try to plot that, but use geom text with only the even years as data. So let's grab our old plot and see how we can modify it as needed. I'm going to grab this. I'll get rid of this so it doesn't confuse you. Okay, and we use geom line, we use geom point. But for this geom text, instead of using our default dataset, which got passed from ggplot here, we're going to give a custom dataset here, which is the even years. So now we're going to pass data here as equal to even years. Okay, whoops, even years. And now when we run this, you'll see that only every other object is labeled there. Only every other point. And maybe 3.3 is a little bit too large. We went a bit too big. Let's go for 2.8 with that. Okay. So now this is starting to look a little bit better. We'll improve it in a number of ways as we go along. So the next thing we may want to do is add alternating labels. So maybe we want to actually display these text labels for all of the years, not just every other year. What we could try to do, and this is a common strategy, is to display those for the even years on top and the odd years underneath the line. So we're going to try to do this now. Okay, and these sorts of labels, that is plentiful labels, are helpful for public health officials trying to interpret the plot. So if they want to be able to look at your plot and pluck out some key numbers that they can use for their policy making, it's nice to give these numbers. So let's go ahead now and filter oslong for the odd years. So we're going to grab oslong here, okay, whoops, and we pipe it into a filter, and we filter where year divided by 2 has a remainder of 1. So year modulo 2 equals 1, all right? And we run that, and that gives us the odd years. And now we're going to duplicate this geom text line of code here. I'll squeeze that all onto one line, and we put a plus, and we grab this, and now we're going to make this odd years instead of even years. Okay, hopefully this makes sense so far. So now if I run this, you will see now that we haven't fixed it yet. So we need to now nudge our odd years downwards instead of upwards. So instead of 20 here, we do minus 20. Okay, and now we have done the needed nudging. But it's still not perfect. So let's see what the next thing we're going to try to do is. Okay, so as you can see, there's still quite some overlap, specifically in terms of the numbers overlapping with the line. Numbers overlapping with the line. Is there any way to prevent this? For that, we're going to introduce you to the ggrepel package, specifically the geomTextRepel function from that package. Okay, so this is going to help us prevent overlap and increase clarity of our plot. So what we're going to do here, I've already loaded ggRepel at the start of the lesson, the ggRepel package. So we can just replace geomText here with geomTextRepel, and we're going to nudge the labels a little bit further up or down. So instead of 20 and minus 20, we're going to use 60 and minus 60. Okay. And let's go ahead and see what this gives us now. So as you can see, you now have much more space between the numbers and the line, such that there's no overlap between the line and the numbers. Our segments here that connect the points to these labels are a bit too large. They distract a bit from the plot. So let's change it to segment.size equals 0.1. Do that for both of these lines. Okay. And now that we run this, you can see that that's starting to look a little bit better. So now you have the benefit of having labels for each of the points, and a policymaker can easily think, oh, in the year 2010, we had 410 cases in urban regions without having to look at your table. They can get this information directly from the plot. Okay. Now let's look at how we can customize this color palette. So this is a default color palette. It may not work for your specific needs. Often you'll want to match your plot colors to your organizational color scheme. Okay. In this case, now we're going to use Scale Color Manual to specify custom colors for each region. So for this, we're going to take our old code here. So this is just copied down here, this same code. And we're going to add a Scale Color Manual. Okay. And the main argument here is values. Values equals C of, and here is the code we're going to use. Okay. The urban areas, we want them to have this hex code as their color. Hopefully you know how to use hex codes. And the rural areas, we want them to have equals to this hex code. All right. And now when we run this, you can see this alternative view. So you may recognize this as one of the Graph Network logo colors. Okay. So far this looks quite nice. Let's add a few plot annotations and theme modifications to make our finalized time series plot there. Okay. So here we add a title, a subtitle, a caption, an x-axis label that is better than the existing one. So we just capitalize Y here to years. And same thing for our color label here. So for region here, we capitalize that. And we use the ggthemes package for a custom theme. And we move the position from where it is here on the right. Actually, we leave it on the right. I think the ggthemes function. Actually, let's run these line by line so you can see what's happening in each case. So first we add all of our labels. Okay, so that looks quite nice now. And then we add the ggthemes theme view, which is kind of a minimalist view. And finally, we try to move this thing here from the... Oh no, actually we don't need this. Legend position equals right is not needed because it's already on the right. Okay, so here is our final plot then. So hopefully you see the value of some of these plot customizations for making a nice presentable time series plot. Now here is a practice question for you. Consider the following plot, which will show the number of child TB cases in 3 countries over time, which we get from the tidyr package. So if we run this to define that data set and then run this line of code, you can see we have this plot showing TB cases in children in Brazil, Chile, and Colombia, What we want you to do is set the geom text labels to alternate above and below the lines, similar to what we saw. Use this color palette for the 3 countries. Use theme classic, and then add a title, subtitle, and caption to provide context on what this data is showing. For our next topic, let's think about how to plot confidence intervals with geom ribbon. So it's often useful to plot confidence intervals in time series visualizations, as you probably know. For this, we're going to use a dataset on new HIV infections in Brazil, which includes estimated numbers and confidence intervals. So let's go ahead and import this dataset. We import it from an Excel spreadsheet using the Rio import function, and we convert it to a table and we clean up the names. So let's take a look at HIV data Brazil. As you can see, you have the continent, the country, the year, which is abbreviated by our markdown here, the sex, and the number of new HIV cases. First as a number, and then as a confidence interval here with square brackets. Okay, so our goal is going to be to try to plot all of this using a geom ribbon. So let's see how we're going to do this. So as I mentioned, you can see that new HIV cases has the cases and the confidence intervals. And we're going to need to extract this into numeric forms because with all those brackets and hyphens, it is obviously a character. So we're going to use the separate function from the tidyverse to split new HIV cases into cases, cases lower, and cases upper. Let me print that dataset for you one more time so you can see that it is composed of 3 numbers, the main number of cases, the upper or the lower confidence interval, and then the upper confidence interval. So let's see how we can separate this using the separate function from tidyr, which is part of the tidyverse. If we press tab, we can see that our first argument here is the column to be separated, and that's equal to new HIV cases. We press tab again, the next argument is into, which is going to be first cases, and then cases lower for this second bit here, and then finally cases upper. Okay, and if we press tab one last time, our final argument is the sep function, or the sep argument, which is going to indicate what characters do we want to look for to do this separation. And in this case, I think we can separate based on this square bracket here and this hyphen. All right, so we're going to try to do that. We open up a set of quotes, and we can do square bracket, open square bracket, or hyphen. All right, but this is not going to work exactly that way because the square bracket is a special operator in regular expressions. So we need to actually escape it in order for that to work. To escape a value, we use this 2 slashes here. Okay, so those 2 slashes will escape this value. Now if we run this, you'll see that it still doesn't work. We've separated cases into cases and cases lower, but this did not work. And that's because there are many different kinds of hyphens, so you have to be careful about your hyphens. In this case, I think this is one of the shorter hyphens. So our best bet is just to copy this hyphen exactly as it is there and paste it in there. And now we know we have the right hyphen. Notice that this one is a bit wider. The one we just pasted in here is a bit wider than that first one. Okay, so we use the pasted in version. And now if we run this, you can see we've separated into cases, and cases lower and cases upper. Cases is abbreviated. Let me make it a longer name, just so it stops being abbreviated for a second. All right, so now you have those 3 values there. Now, of course, we're not quite done yet because these are still classed as character values, cases lower, cases upper, and cases. So we're going to need to parse them into actual numbers. But before we get to that, one small note is that this kind of regular expression may look quite scary to you, and indeed it is quite scary to me as well. But large language models like ChatGPT are great for understanding and generating these sorts of regular expressions. So if you get to a bit like this, and you know you want to separate this line of, or this kind of character, you can just ask ChatGPT, please give me the necessary regex to separate this by an opening square bracket or a hyphen, and it'll help you realize that you have to escape this and that you have to use the or symbol and so on. And if you get an error, you can give it back to ChatGPT and have it help you out. Okay, So no beginning student really should be learning regex any longer, only if you're really trying to do very precise things that you should be learning regex or regular expressions. Just use the LLMs because that's what they are perfect for. Okay, so now let's go ahead and try to convert those characters into numeric values. All right. So we have already separated this now into cases, cases lower, cases upper. Okay, and I think here we're missing the sep argument, so let's put that back in there. Sep equals. All right. And now what we're going to do now is we pipe this into a mutate, and we're going to use the across function within that mutate. Hopefully you remember how to use this. We indicate the columns that we want to change, which are cases. Maybe we don't need actually that those apostrophes anymore, so we can just type like this. All right. And we indicate the function or sets of functions that we want to use to manipulate I can't see them anymore. Let me just run this so you can see them. To manipulate these numbers. Okay. So here's the set of functions we're going to use. We're going to say str, or we define a function using this anonymous tilde syntax there. Str remove all. Okay. Dot x, where dot x will stand in for any of these columns. And remember that this tilde here is standing in for function defined on dot x. Hopefully you remember some of this. So we put the tilde back, str remove all. And what are we going to remove from each of these? We're going to remove any non-numeric characters. And the way you represent numeric characters in regular expression is you say 0 to 9 with these brackets here. So now you can see why this is a special character here, because it represents, for example, this whole sequence. But we want to remove anything that's not numeric, so we put this hat here, and that'll give us not numeric. And at the same time, we're going to pipe this. After you remove these random strings, you then need to convert that to numeric. So maybe I'll just nest this. So as numeric of all of that. And I'll comment out this top line just so we can run this and see the output. And indeed, you can see these are now doubles, which means they are now numbers. So it seems to have worked. We can assign this to HIV Brazil clean, remove some of these scaffolding comments, and now we are ready to do our actual plotting. Okay, so we're ready to plot the data using geom ribbon to display our confidence intervals because we have all of them in the needed numerics. So the first thing we're going to do is filter to show just one type of value here. You can see there's female, male, and both sexes for each of the numbers. Let's start by plotting both sexes. So we say sex equals both sexes. And then we're going to plot cases on the y-axis versus year on the x-axis. So pipe that into ggplot. And within our aesthetics, we're going to have y equals cases. And on the x-axis, we have that as the year. Let's get rid of some of these comments to make it a bit easier to see what we're doing. Okay. Now if we run just this, okay, you can see that at the moment it's still empty because we need a geom line. So geom line. And let's go ahead and run that. And now we have the line graph of the cases over time. Okay. Now what we need to do is we need to plot our geom ribbon with ymin and ymax. So this is the moment of truth, so to speak. So we say now geom ribbon, and we give this the special set of aesthetics ymin and ymax. Ymin is the lowest portion of our ribbon, and that will be, of course, equal to cases lower. And ymax is the upper portion of our ribbon, which is equal to cases upper. Okay, so ladies and gentlemen, after all of that work now, here is the plot that we are looking for. It's quite ugly for now. Let's add an alpha to make the ribbon a bit less opaque. So alpha equals 0.4. Okay, so now that's much more nicer looking. So now let's go ahead and try to create separate ribbons for men and women. This is the plot for all sexes. Let's see if we can create separate ones for men and women to, for example, compare infection trends. So here we're going to filter and drop the both sexes. Filter sex not equal to both sexes, otherwise known as sex equal to male or female. And then I'm just going to copy a lot of this stuff here because it will be the same. Okay. And the only thing we're going to add here is a color here, color set to sex. And let's go ahead and run this just to see what that looks like first. And as you can see, the colors of the lines now have been changed by the sex. But we also want to fill in this portion of the ribbon based on sex. So we add now a fill equals sex aesthetic mapping in there. And now that looks much better. And you may notice that, importantly, the number of HIV cases in women peaked at around 2008 to 9 and then has been dropping. But the number of HIV cases here in men in Brazil has kept on rising since then. Now here is a practice question for you on plotting confidence intervals. Consider this dataset that shows the number of annual malaria cases in Kenya and Nigeria. If we import it, you can see that you have a country, you have a year, and then you have the malaria cases variable that has the estimate from the number of cases, and then the lower and upper confidence intervals. So what we want you to do is parse all of those numbers and plot them as confidence intervals using Geom Ribbon. So pause the video and try that out. Now let's think about smoothing noisy trends. So analyzing time series data often involves dealing with noise and with variability. And smoothing techniques can help to highlight important trends and patterns. To do this, we're going to look at an example of some line list data on pediatric malaria admissions in Mozambique. So before we get to actual smoothing of the trends, we're going to see how to generate an incidence table from this line list data. So if we run all of this code here, we can take a look at the MAU dataset here, which has the date of a positive test for each child, the neighborhood that child comes from, their sex and their age in age groups like 6 to 11 months, 5 to 14 years, and so on and so forth. So this is a line list. This is not yet any kind of time series data, but you can easily convert it to time series data in the following way. To create an incidence table, we're just going to count cases by day using the count function from the tidyverse. So we pipe MAU here into count, and we count the date positive test variable. And if you run this, you can see you have date positive test and this n variable that indicates the number of cases for each day. And we can rename that to, say, just cases. And let's pipe this into cable so we can see it more fully. So you can see now that for each date you have the number of cases, 67, 120, and so on. However, there's one small problem with this, right? And that is that it has some missing dates. So any date where there wasn't any recorded case is currently missing from the table. Let's take a look at that one more time. You can see, for example, here that between 0119 and 0122, there are two missing dates, and they have no values here. So that's not a very nice epicurve. That's not a very nice incidence table. It would be nice to fill those in with the value of 0. So it's clear that this dataset contains all of the days in question. Okay. So to do that, we're going to use the complete function and fill in with zeros. So let's see how we do that. We pipe now MAU into count notif into count, just as we did up there. And then we're going to pipe this into the complete function. And what do we want to complete? We're going to say date positive test is equal to seq.date with the capital D there. That's seek date, okay? And we're going to go from equals the minimum date in our dataset MAU. So minimum MAU date positive test to the maximum of MAU date positive test. And let's just see what each of those are. So you can see we're trying to go from, let's start with the min, trying to go from 2019-01-01 all the way to 2020-02-10. All right. And we need to indicate by how many increments are we moving that sequence. And that's just day by day. So by is equal to day. All right. The last argument we need is what to fill in our data with. And for that, we give it as a list. So fill equals list, cases equals 0. Okay. And now I'm going to run this. Now notice that this complete function is probably one of the first times you've seen it. So if you want, you can pause the video and look at the documentation of that so you really understand what complete is doing there. But for now, I'll go ahead in the interest of expedience and I'll run this so we can see now that malnotif count here has for each date positive test still the cases, but missing dates now have been filled with 0. 0106 filled with 0, 0109 filled with 0, and so on. So this seems to have done what we wanted it to do. So now that we have a valid incidence table, we can go ahead and plot our data. So this says this results now in a complete incidence table with data for 406 consecutive days. So we're going to be able to plot this data to reveal the overall trend, but we're going to see that it's quite noisy, and this is where our data smoothing will come in handy. So let's go ahead now and plot ggplot of malnotif count, a line plot with cases against date of positive test. All right. So we say ggplot of malnotif count, and let's print that just so we can see what we're plotting. We do geom line here, okay, and within the aesthetics, we're going to say our x-axis is equal to date of positive test, and our y-axis is equal to the number of cases. And we can run this now, and you can see that plot. So this is showing the number of daily recorded malaria cases in this pediatric population. But as you can see, it's really quite noisy. It's not very aesthetically pleasing. It's kind of hard to tell the specific trends that are visible, and it's overall not a great thing to plot. So this is where the idea of smoothing is going to come in handy. So let's see what we can do in terms of smoothing this data. The first thing we can do is we can use the geom smooth function. So geom smooth will use LOS, which stands for locally weighted scatterplot smoothing by default, to smooth the line that gets plot. And let's see how it smooths out this specific time series. So we're going to copy this code here, and we're just going to replace our geom line there with geom smooth. So instead of geom line, we have geom smooth. And let's see what that gives us. And maybe for to make this easier to read, I'll pull this out and put this up here within ggplot rather than within geom smooth. So if I run this now, you can see it's a super smoothed out line showing the distribution of cases over time. Okay, and like I said, what LOS does is it fits a smooth curve by calculating the weighted averages of nearby points. You don't really need to understand the math behind this, but it's important to know how to adjust the sensitivity of the smoothing. You use the span parameter for this, the span argument within geom smooth, where a lower number gives you more sensitivity and a higher number gives you less sensitivity. Let's see how to do this. We're going to try some spans between 0.1 and 0.9. Notice here that we set method equals to LOS explicitly. This is the same thing as just not defining any argument there. Method equals LOS is just making it more explicit because the default method is LOS. There are some others, but for now we're sticking with the LOS. So now let's adjust the span. So we say span here equals, let's try something like 0.1. You can see now that this is much more sensitive to the specific variations of our data set. If we go up to 0.3, it's becoming a bit less sensitive. If we go to 0.9, you can see it's now super insensitive to the variations, only tracing out the very, very broad trends. Hopefully that makes sense on what the span parameter there is doing. Now let's think about how you can smooth by aggregating. So aggregating data will let you clump up your data into larger time intervals, and this is something you already did at the start of the lesson, where we took the quarterly data in Australia and aggregated that to yearly data. Let's look at this example here where we're going to take the daily data from malaria and aggregate that into monthly. So remember we made this plot here, which was, where's that plot? Which had daily data and is quite noisy. And we might want to aggregate it to monthly instead. So let's see how we can do this. So our goal is to group by month, and we'll start by converting the daily malaria cases to monthly using floor date. So let's see how to do this. We have malnotif count, which has each of these full dates, and we want a way to have every date in January have the same value so we can group by that value. The best way to do that is using the floor date function from lubridate. So we say floor date of date positive test, and we want to floor the date to the nearest month. And if you run this now, and we pipe it into cable so we can see it properly, you can see that all the dates in January from 2019, 01, 01, all the way to 0131 all have the date floor of 2019-0101 or January 1st, 2019, and so on and so forth for the other months. So now we have a date that, or a variable that is the same for all the dates in January and for all the dates in February, and so on. And we can group by and summarize for total cases per month using this specific variable. So let's go ahead and do this now. We pipe this into group by, and we group for each month. We want to summarize where cases is equal to the sum of the cases in that specific month. And we can print monthly just to see what that looks like. Let's pipe it into cable. You can see now for each month you have the total number of cases. So now let's see how we can go ahead and plot this data and see what it looks like. So we take our monthly and we're going to put that into a ggplot. And we plot a geom line. Again, our aesthetics will be the same. So x is going to be equal again to our date positive test. And our y now is equal to the cases, but this is a summarized cases, or monthly cases. Whoops, there's a mistake. What mistake did I make? Sorry, monthly no longer has date positive test, it has just month. So we plot it against the month. And if you run this now, you have a much less jagged plot, and it's a little bit easier maybe to see the overall trend. So this is one way of smoothing out your data. So now that you have that in hand, try this practice question on smoothing HIV death data in Colombia. So this is data on individuals who died from HIV-related outcomes between 2010 and 2016 in Colombia, the country in South America. And it's a line list again. So what you have to do is convert the line list into an incidence table that counts HIV-related deaths per month, plot an epi curve of the deaths per month, and then apply geom smooth for a smoother visualization. So pause the video and try that out. Let's look at another way of smoothing, and that's with rolling averages. So rolling averages can be used to smooth noisy time series data. And the way we do this in R is using the roll mean function from the zoo package, which is generally used for calculating different sorts of rolling functions. So the zoo package provides us this roll mean function, and we're going to use it to calculate the 14-day rolling average for our daily malaria case data. So let's see how to do this. We're going to make a new column called roll cases, and that is going to be the roll mean of the x vector that we want to do the roll over, and that's going to be equal to our number of cases. Let me print malnotif count so I have that in hand. So yes, x is the number of cases. Then k is the number of days we want to average over. In this case, we're going to pick 14. And fill is what we want to fill in any missing values for. I'll show you what we mean by that in a second. And now we can run this. And we're going to print and view malnotif count, the updated version. I'll pipe it into cable. And what you'll see here is, first of all, the first 6 values are NA, and we'll talk about that in a second. But let's take this 7th value here, which is 83.42. What that is the average of a 14-day window where 7 days are in front and 6 days are behind. Okay, so these 7 days here, including the date itself, 115 plus 0 plus 85 and so on, divided by 7, and all of this as well divided by 7. So all these numbers here, but in the test case, in the cases column here, divided by 14. Hopefully that makes sense on what that rolling average is doing there. And now we can think about, why are these NA values there, these NA values for the first 6? Because the sliding window relies on at least 6 values being behind the specific index. These must be NA because there aren't enough values to actually fill in that average. Okay, so because there are those missing values there, you can't get the rolling mean for those cases. Hopefully that makes some sense. Now, like I said, the key arguments for roll mean are x, which are the time series data you want to smooth, k, which is the number of points you want to average, and fill, which indicates how to handle missing data in each rolling window. So now let's go ahead and plot this data. We're going to plot, instead of cases, we plot now roll cases. And as you can see, this smoothed line is a bit more clear in terms of the specific trends than our original daily plot. Now, more commonly in public health, your sliding window will want to refer to the past 1 week or the past 2 weeks. So usually you're asked to plot a rolling average of the past 1 or 2 weeks. And to do this, you set align equals right. You can remember, for example, during COVID, when on a specific day, let's say it's a Wednesday today, instead of just reporting the number of new cases on that specific Wednesday, the news agencies and public health agencies would report the average for the past 7 days. So Wednesday and Tuesday and Monday, all the way back to the past Wednesday. And this gives you a more smoothed view of the daily variation in cases to avoid the noisiness that comes with, for example, when the number of cases drops during the weekends, which you may have remembered from COVID. In any case, it is usually important to plot the past 1 or 2 weeks when you're plotting these sorts of rolling cases. This is very easy with row mean. We're just going to set the align function equal to right. And this will align your rolling window to the right and give you the past, in this case, 2 weeks. So if we run this now, and let's view our output, here you can see now that the first 13 dates are NA, because those 13 dates don't have past 13 dates to take the average 2 weeks of. Okay, so we start with this value here on the 14th of January, and there we have the rolling averages for that. If you set this to 7, then you would have just the past 6 days being missing. So just as I said, with align equals right, the first 13 days are NA because they don't have up to 14 days before them. Okay. Finally, let's go ahead and plot our original and our smoothed data to compare them on the same axis. As you can see, this smoothed data in red there is clearer to observe the main trends. So here is a practice question for you on smoothing with rolling averages. So consider again this data set of HIV patient deaths in Colombia. Okay. And this following code here calculates the number of deaths per day. But it's going to be a very noisy data set, 1, 0, 1, and so on. So what we want you to do is simply create a new column that calculates the rolling average of deaths over a 14-day period and plot this rolling average alongside the raw data. So pause the video and try that out. Now our very last topic here is going to be secondary axes. Secondary axes are useful for visualizing two different measures with distinct scales on the same plot. And this is often frowned upon by data visualization experts, but within public health it is actually often appreciated, especially by public health decision makers who like to be able to see their key numbers and charts sort of squished into as little space as possible so they can make quick decisions. So a very common example of the kind of secondary axis plot we are asked for in public health data visualization is plotting daily and cumulative cases on the same plot. We're going to do this using our MAL dataset, plotting daily malaria cases and cumulative malaria cases on the same ggplot. To do this, we'll start by creating the cumulative case counts variable for malaria. That is, we aggregate the cumulative counts over time. You'll see what that means in a second. So let's see how to do this. We're going to take our MAL notative count dataset, which has the number of cases and row cases, which we don't care about for now. So just focus on the cases. And we're going to say mutate, and we'll add a cumo cases variable, and that's equal to the function cumSum or cumSum of just cases. Okay, and let's drop row cases just so that it doesn't confuse us in the output. So we drop this. And now let's see what that looks like. So notative count cumo, I'll pipe this into cable to see that output. And as you can see now, the cumo cases is a cumulative running count of the past cases. So for the first day, it's 67. For the second day, it's 187, which is 120 plus 67. For the third day, it's 299, which is 112 plus 120 plus 67. And so on and so forth, infinitely, or not infinitely, at least until the end of the data set. So hopefully that makes sense what that cumulative variable is doing there. So now we're going to try to plot both the daily cases and the cumulative cases on the same y-axis. And in doing so, we'll show why we need a secondary y-axis sometimes. So let's see how to now plot these two variables. So we're going to take now our new dataset, notative count cumo, and put that into our ggplot. And we're going to say geom line geom line. Our first line is going to take the regular cases. So x equals, what's x equal? Let's look at our data set again. Date positive test. And y equals cases. And then we make a second line, second geom line. Okay. And here we set our y equals cumo cases. Okay, now if you run this, you can see you have two lines. This big one is the cumulative cases, and this tiny one is the cases. And as you can see now, you can barely tell what is going on with the cases any longer because it's been really squished relative to the cumulative cases. So these two data sets really can't be shown on the same plot because their scales are so vastly dissimilar. So what can we do? Well, we're going to add a secondary axis. The first step for adding the secondary axis is calculating a scale factor that will you calculate by comparing the ranges of the two different variables you're trying to plot. In this case, cases and cumulative cases. So we do this first by checking the maximum value of the cases, which is 419. So on a specific day, there were 419 cases in one day. And the maximum cumulative cases, which is 20939. So at the end of the data set, you had 20939 total people ever having been diagnosed with malaria. So our scale factor is going to be this bigger number here divided by the smaller number. And if you run this, we can see that that's roughly 50 or 49.97. So one set of numbers is roughly 50 times larger than the other set. So we're going to use this number 49.97 throughout our manipulations. So the first step we're going to do is we're going to divide this cumo cases by this scale factor, 49.97, to get it about as small as the cases. So let's plot it without dividing first. So as you can see now, we have this red line, cumo cases, and then the black line, which is the cases. Now if we divide this though by our scale factor, now as you can see, they have about exactly the same highest point because we divided them by the ratio between their highest points. So these are now both visualizable on the same axis. Hopefully that makes sense. So now what we've done is we've divided the bigger number by this scale factor, or the bigger time series by that scale factor. But now our problem though is that our y-axis no longer tells us information about this red line. So we're going to need a new axis for the red line. Before that, a small side note. Okay, so normally you would store the scale factor in a variable and then plug that in. But here we're doing it manually just to make it a bit easier to understand and keep track of what's going on. Okay, so this thing here, normally you'd store in some kind of variable, blah, blah. But we're using it manually like this to make it easier for you to understand what's going on with the scaling, because the topic is hard enough as is already. So now let's see how we can add the secondary y-axis to make this red line have a partner that indicates what is actually showing. Okay. For this, we're going to use the sec-axis function from ggplot2, which has a trans argument, which stands for transformation. So let's see how to do that. It also has a name argument, though that's not as important. So here's the code that we had from the previous code chunk. To this code, we're going to add scale y continuous. Okay, and we're going to use the sec.axis argument equals to sec.axis as a function. And sec.axis as a function has two main arguments, or really one main argument. That's the transformation you want to apply. The transformation we want to apply, remember, is we're going to try to make this y-axis larger than its equivalent on the other side. So here, the maximum is about 400, but the maximum on this side should be about 20,000. So 400 times 50, or times our scale factor. So we're going to use an anonymous function here, okay, that says take the values, dot x there, and multiply them by, what was our number again? 49.97. 49.97. And remember that this here just means a function on x, okay, that takes x. In fact, let me just pull this out and write it as a custom function for you here. We call it times scale factor, or scalar, okay, and that's a function defined on x, and it returns x times our scale factor. Okay, hopefully that makes sense. By now you should know how to use functions. So we say trans is equal to our scalar, okay? And we give it a name. Our name is just going to be cumulative cases. All right. Now if you plot this, okay, you can see now that you have our transformation where the maximum here is about that 20,900 and something, okay? And this now applies to the red line. Okay, hopefully that makes sense. And I'll bring back my anonymous function here because it's a bit easier to write this as an anonymous function. This was just to demonstrate what's going on. So put that back as an anonymous function. We get rid of the function definition, run it one more time, and make sure it's still running. Okay, so now as a last step, let's try to enhance the plot readability. So we do a number of things. We set a title and a subtitle. We use the theme economist. And most importantly, we set axis text and axis title on the right to be red so that it matches this red line. Those are the most important bits. Let's run these section by section. So I run first just this, Control Enter, and that gives us our plot that we had before. Then we add some titles and subtitles, and that gives us that. Then we use theme economist, which is one of my favorite themes from GG Themes. And that gives us that nice economist-y plot. And finally, we set our right axis to be red. And there's our final beautiful plot. So in conclusion now, you've learned how to add a secondary y-axis to your plot, enabling comparison of two datasets with different scales in a single visualization. Now here's a practice question for you on secondary axes. So revisit the column HIV deaths per day object, which you defined in a previous question. And what you're going to do is just create a plot with two y-axes, one for daily deaths and another for the cumulative deaths in Colombia. So pause the video and try that out. So congrats on getting to the end of the lesson. Let's take a look at our learning objectives and see if you feel confident with these. So the hope is that now, by the end of the lesson, you are now able to reshape time series data for plotting using the pivot longer function, that you can now create line graphs in ggplot2 by mapping time to x and values to y. Hopefully that's now easy for you. You can enhance those line graph aesthetics using techniques like custom labels, color palettes, and annotations. You can visualize confidence intervals using geom ribbon. You can highlight patterns in noisy data using smoothing and aggregation. And finally, that you can compare time series with distinct scales using dual axes and the sec-axis function from ggplot2. So congratulations again, you have now developed key skills for wrangling and visualizing time series data and improving the aesthetics of your time series plots. These are skills that will come in super handy throughout your data analysis career. I hope that you keep wrangling, keep plotting, and keep practicing, and I'll see you in a future lesson. Bye-bye.
For more resources, visit our website, where you can track your progress, access interactive quizzes and lesson notes, and connect with our teachers and other learners like you. And if you'd like a more guided experience, we also offer live online bootcamps with expert help. So join us at thegraphcourses.org to start your learning journey today.